Hello class, this lesson will deal with the fire pump, chapter 5 in your textbook. This lesson will discuss the basic principles underlying the use of pumps in the fire service. Pumps are vital to the operations of firefighting. Without them, firefighters would be unable to discharge water under pressure to extinguish fire. As the driver operator of the fire department pumper, you must understand how pumps operate so that you will be able to fix any problems that you may encounter on the fire ground. As stated earlier in our class, all exam questions are mapped to the learning objectives. Students should thoroughly understand the learning objectives to be successful in this lesson. So let's review our learning objectives. By the end of this lesson, you should be able to explain the importance of understanding the fire pump and its systems, describe the exterior and interior features of a pumper, define the term pump, explain the basic operations of positive displacement pumps and centrifugal pumps, explain the different types of positive displacement pumps, explain the different types of centrifugal pumps, describe a single-stage pump and a two-stage pump, describe the intake side of the pump, describe the discharge sides of a pump, describe the pump valves and drains, and describe the components of the pump panel. Pumps are vital to the operations of firefighting. Without them, firefighters would be unable to discharge water under pressure to extinguish fire. The driver operator must understand how pumps operate in order to fix any problems they may encounter on the fire ground. The fire service has an old saying, and I quote, "Don't just be a knob puller. Know what you are doing," end of quote. Do not just memorize a specific sequence of tasks to operate the fire pump. Ensure that you have a thorough understanding of how each pump operates. For example, if you understand that a centrifugal pump is capable of pumping only fluids and not air, then you will know that you have to prime the pump before it can operate. Let's talk about the exterior of the fire department pumper. The fire department pumper is, essentially, a large fire pump with hose and tools to extinguish fires. The pumper is the most common fire apparatus, being found in almost every fire department's fleet. The cab of the fire apparatus, where the firefighters ride to the emergency, sits on a steel frame. Attached to this frame are the storage compartments and the fire pump. The compartments on the fire apparatus hold all of the various tools and equipment needed for firefighting operations. Ground ladders may be mounted on the side of the apparatus on a side-mounted ladder rack, which is a stowed position, is on the top of the apparatus, in a special compartment in the hose bed, adjacent to the hose bed, or in a through the tank compartment. Supply hose and attack lines are stored in the hose bed, which may be either left uncovered or covered with a tarp to protect it from the elements. Some fire apparatus may provide a metal cover to further protect the hose. Most pumpers carry pre-connected attack lines for quick deployment of such lines. These hose lines are usually located above or on the side of the pump panel. The pump panel is the most notable device on the fire apparatus. It is usually covered in stainless steel and has multiple levers and gauges mounted on it. Although this panel might be seen intimidating to the new driver operator, once you have a thorough understanding of the pump behind it and the functioning of this system, you will be capable of confidently operating the fire pump. Let's discuss the interior of the fire department pumper, the cab. Inside the cab of the pumper, you will find all of the necessary controls to operate the fire apparatus. When you are sitting in the driver's seat, many of the controls and features will seem similar to those found in any other large vehicle. There are switches to operate the seats, mirrors, headlights, and windshield wipers, just as in any other vehicle. Some of the controls, however, are very different. For example, the controls to engage the fire pump or operate the emergency lights will not be found in other types of vehicles. It is important for the new driver operator to understand that the fire apparatus is not like any other vehicle and, therefore, should not be operated like other vehicles. Fire pumps. A major component of fire attack is water. To get the water on the fire, you must first pressurize it. To do this, you need a fire pump. NFPA 1901, which is the standard for automotive fire apparatus, defines a fire pump as a water pump that is mounted on the fire apparatus and used for firefighting. The fire pump must be capable of delivering a minimum of 250 to 3,000 gallons per minute at 150 pounds per square inch net pump pressure, or over 3,000 gallons per minute at 100 psi net pump pressure. When the fire apparatus is designed to pump and roll operations, the fire apparatus engine and the drivetrain must be arranged so that the unit can pump at least 20 gallons per minute at a gauge pressure of 80 psi while the fire apparatus is moving at a speed of 2 miles per hour or less. Some fire apparatus are designed for responding to small vegetation fires and have relatively small capacities because they do not carry large amounts of water. These devices are usually mounted on the fire apparatus and have a separate engine to power them, other than the one that drives the fire apparatus. Other fire pumps are operated in a stationary position. They tend to be much larger and have a greater capacity. These fire pumps, which are typically used to combat fires that involve structures such as homes and commercial buildings, are powered through the transmission in the fire apparatus engine. Still, other fire pumps may be equipped with pump and roll capabilities. No matter what size the fire pump, it must meet certain requirements. For example, NFPA 1901 states that if the pumping system is rated at 3,000 gallons per minute or less, it shall be able to deliver water at the following rates: 100% of rate capacity at 150 psi net pump pressure, 70% of rated capacity at 200 psi net pressure, and 50% of rated capacity at 250 psi net pressure. These requirements indicate that the minimum amount of water, or GPM, the fire pump can deliver is at 150 psi net pump pressure. As the fire pump's psi rate increases, the amount of water that can be delivered decreases. After the fire pump reaches capacity, the only thing to gain by increasing the revolutions per minute, or the RPM rate, is an increase in pressure. This information may be useful if you are supplying attack lines for a high-rise fire and need the added pressure, but not the entire capacity of the fire pump. While drafting, if the fire pump is rated at less than 1500 GPM, it is capable of taking suction through a 20-foot of suction hose and can discharge water in less than 30 seconds. If the fire pump is rated at greater than 1500 GPM, it is capable of taking suction through 20 foot of suction hose and can discharge water in less than 45 seconds. Larger fire pumps are allowed more time to operate from a draft because they have more space inside that must be exhausted of air before water can enter the pump. The fire apparatus manufacturer shall certify that the fire pump has the capability to pump water at 100% of the rated capacity at 150 psi with a net pump pressure from draft through a 20-foot section of suction hose with a strainer at an atmosphere 1,000 feet above sea level, an atmosphere pressure of 759 millimeters of mercury, and a water temperature of 0 degrees Fahrenheit. The size and number of suction lines required vary according to the size of the fire pump. All fire pumps are rated from a draft. This means that no added water pressure from an external source is used to offset the capacity of the fire pump. The pump test is usually conducted at the manufacturer by a third party, for example, to determine Underwriter Laboratory certification. Once you engage the fire pump, you need to have a mechanism to ensure that it is running. When a separate engine is used to drive the fire pump, an indicator light in the driving compartment is illuminated when the fire pump is running. This indicator light is marked with a label such as pump engine running. If a fire apparatus is equipped with an automatic chassis transmission, the fire pump is driven by the transmission. This type of fire pump is used for stationary pumping only. A pump engaged indicator in the driver-operator's compartment signals when the pump shift process is complete, and an OK to pump indicator in the driver-operator's compartment identifies when the fire pump is engaged. A separate throttle ready indicator is provided at the pump panel to signal when all necessary steps have been taken to ensure proper safe pumping. Other indicators of pump engagement include that the speedometer in the cab is operating and that the pressure is indicated on the master discharge gauge of the pump panel. NFPA 1901 defines the requirements of fire apparatus equipped with water tanks. Depending on the type of fire apparatus, the water tank may hold several hundred or several thousand gallons of water. Each fire department should carefully evaluate its water supply needs and the available water delivery systems when considering the size of water tank on the fire apparatus. Regardless of the tank size, NFPA 1901 states that all water tanks shall be constructed with non-corrosive materials or other materials that are treated against corrosion and deterioration. In addition, all water tanks should be equipped with a baffling system with a minimum of 2 transverse or longitudinal vertical baffles that cover at least 75% of the area of the plane that contains the baffle. Each tank should include one or more clean-out sumps with 3-inch or larger removable pipe plugs. Plugs are often used to clean out the silt and debris that may become trapped in the water tank over time. NFPA 1901 covers many other aspects of water tanks. For example, the water level indicators, the tank-to-pump intakes, the filling, the venting, and the external filling issues. Fires are extinguished when the proper amount of water, or GPM, is applied to the fire. This volume of water is directed through a nozzle at the required pressure to give the fire stream enough reach so that it can penetrate to the seat of the fire. A pump pressurizes the water used to attack the fire. According to the 2013 edition of NFPA 20, which is the standard for the installation of stationary pumps for fire protection, a fire pump is defined as a provider of liquid flow and pressure dedicated to fire protection. It is a mechanical device used to move fluids. This concept is very important for firefighters because they want the pump to move the water from the source, such as an onboard water tank, to the fire through the attack lines. One of the first things to understand is that pumps alone do not create pressure. Pumps displace the fluid, which causes this fluid to move or flow. Resistance to this flow, in turn, creates pressure. With higher pressures, you will have less volume or flow. With higher flows, you will have less pressure. Pumps cannot provide both high pressure and high volume of water at the same time. Let's now talk about the various types of fire pumps that are used in the fire service. The fire service primarily uses 2 types of pumps: positive displacement pumps and centrifugal pumps. Each type relies on different operating principles and offers a different set of features. Let's talk about positive displacement pumps. According to NFPA 20, a positive displacement pump produces a flow by capturing a specific volume of fluid per pump revolution and reducing the fluid void by a mechanical means to displace the pumping fluid. It traps a fixed amount of fluid and forces that amount into the discharge stream during every revolution of the pumping element. The pump displaces the liquid by creating a space between the pumping elements and trapping the liquid in the space. As the pumping element moves, it reduces the size of this space, which in turn forces the fluid out of the pump. Positive displacement pumps rely on tightly fitting parts to function properly. Models are self-priming, however, they still require proper conditions, such as no excessive air leaks, to function properly. They can move air or water during every revolution because the parts fit together so closely. They are an ideal choice for use as a priming pump for centrifugal pumps. As a priming pump, the positive displacement pump is connected to the top of the centrifugal pump. When the positive displacement pump is operated, it draws air and water from the top of the centrifugal pump until a constant flow of water is achieved, thereby ensuring that only water is inside the centrifugal pump casing. Positive displacement pumps may also be used as high-pressure auxiliary pumps or portable pumps. Because their efficiency depends on their close-fitting moving parts, the performance of these pumps will begin to deteriorate as they wear down over time and with excessive use. The presence of sand and other debris can cause the moving parts to wear out prematurely, further diminishing their performance. The two broad classifications of positive displacement pumps for firefighting purposes are the piston and the rotary pump. Rotary pumps exhibit a circular motion. Piston pumps have an up and down action. Piston pumps. They use a cylinder to contain the fluid. A piston then moves back and forth inside the unit to move the liquid out of the cylinder. As the piston moves, water is drawn in from the intake side of the pump and expelled out the discharge side of the pump. This output of fluid is directly related to the RPM of the piston. As the piston moves faster, the liquid will be discharged faster. Piston pumps class have three moving parts: the piston, the intake valve, and the discharge valve. Inside the cylinder is the piston. The piston creates a seal in the cylinder to separate the intake side and the discharge side of the pump. Intake and discharge valves create or block the respective openings so as to direct the water toward the target. Two types of piston pumps are available: single-acting piston pumps and double-acting piston pumps. Let's talk about the single-acting piston pump. The operation of a single-acting piston pump is very simple. This type of pump has one intake side and one discharge side, both of which are located at the same ends of the cylinder. As the piston moves upward, away from the intake side, a vacuum is created in the cylinder. This vacuum causes the intake valve to open and fill the cylinder with water. Water continues to fill the cylinder until the piston stops. At the same time, at the discharge side of the pump, the discharge valve remains in the closed position. Once the piston moves in the opposite direction, the intake valve closes and the discharge valve opens to expel the water. The single-acting piston pump is similar to a squirt gun. As you depress the trigger, water inside a cylinder is compressed and discharged out the tip. When you release the trigger, the cylinder refills with water and waits to be discharged again. With every pump on the lever, a definite amount of fluid is discharged from the single-acting piston pump. Water is discharged only on the downward movement of the piston, which creates a pulsating effect because water is not constant. As a consequence, class, single-acting piston pumps are not suitable for use on an attack line. The fire stream from this type of pump would be inconsistent and have moments without any water discharged. An additional piston can be added to increase the water flow and provide a more constant flow. With this setup, the two pistons would operate in opposite directions to maintain the water flow. While one piston is filling with water, the other would be discharging the water. A double-acting piston pump allows water to flow more continuously than a single-acting piston pump while using only one piston. It has periods of limited flow, specifically when the pistons are at the top of their stroke before changing direction. The pump has both valves at each end. As a consequence class, the cylinder fills with water on both the up and down strokes of the piston. When the piston is pulled upward, the water flows into the cylinder through the intake valve. At the same time, water flows through the discharge valve on the other side of the piston. Rotary pumps typically are used as the priming pump for a centrifugal pump. They operate in a circular motion and discharge a constant flow of water with each revolution. To accomplish this task, some pumping element, such as a gear or vane encased in the pump casing, rotates, expanding the volume inside to allow the water to enter the pump. As the pumping elements rotate, the area in which the fluid is contained is reduced, which in turn forces the water out of the pump. This results in a smooth, continuous flow of water discharge from the pump. The internal components fit together tightly and allow for very little water to slip back from the discharge side to the intake side of the pump during operation. Rotary gear pumps are a type of positive placement pump commonly encountered in the fire service. They are typically used as a priming pump. The rotary gear pump uses two gears, most often driven by a 12-volt electric motor. Inside the pump casing, two gears rotate in opposite directions. Gears are positioned closely to each other and to the inside of the pump casing, forming a watertight seal. As the two gears mesh together, they trap water and move it to the discharge side of the pump. Usually, a motor powers one gear, which then powers the second gear. Oil may be fed into the pump to maintain as watertight a seal as possible. The oil will fill any open spaces to make the pump work more efficiently. Rotary vane pumps use small movable elements called vanes, which freely move in and out of the lots of the rotor to maintain a tight seal against the pump casing. The vanes are positioned off-center inside the pump casing and automatically maneuver in and out to compensate for changes in the pump casing. As the vanes approach the intake side of the pump, the void space increases and the vanes slide further out of their slots. Water then flows in between these vanes, becoming trapped there. When the vanes approach the discharge side of the pump, the void space decreases and the vanes slide further back into their slots. Water that is trapped in between the vanes is then discharged from the pump. Because the vanes in the rotor move independently as the surface of the vane itself wears down over time, it will continue to maintain a watertight fit. It can automatically adjust itself to compensate for the wear and tear in the unit. Centrifugal force keeps the vane tightly pressed against the pump casing, thereby ensuring a tight seal. This makes the pump operate efficiently. The most common fire pump in use today is a centrifugal pump. This type of pump has largely replaced positive displacement pumps on modern fire apparatus. They do not flow a definite amount of water with each revolution. Instead, the flow or amount of water discharged is based on the pressure at the discharge side of the pump. At higher flow rates, the pump will flow less volume but will create higher pressures. As the pump spins more slowly, it will create less pressure on the discharge side but will flow a greater volume of water. This flexibility makes the centrifugal pump a very versatile piece of equipment on the fire ground. As the driver operator, you need to understand how this pump works to maximize its potential as part of firefighting operations. This pump operates on the basic principle of centrifugal force, that is, the outward force from the center of rotation. This pump receives water into the center or eye of an impeller that is mounted as an offset inside the pump casing. The pump impeller forms the heart of the pumping device. This metal rotating component transfers energy from the vehicle's motor to discharge the incoming water. Inside the impeller are impeller vanes, which divide the impeller. As the impeller spins, it accelerates the movement of water between the vanes and discharges the fluid radially outward into a collection area called the volute. The volute gradually increases in area, causing the water pressure to increase. It then directs the water into the discharge header when piping is attached and valves are arranged to deliver water to the intended hose lines or devices. A centrifugal pump can pump only water or other fluids. It is completely devoid of any valves from the intake to the discharge side. Water is free to move between either side of the impeller when it is not spinning. When the impeller is spinning, the water is taken from the intake side and flows out the discharge side. If the discharge valves are all closed, the water inside the pump simply churns around inside. The centrifugal pump relies on the movement of water from the intake side to the discharge side to operate efficiently. Unlike a positive displacement pump, this device is not self-priming. Therefore, the centrifugal cannot pump air, only liquids, typically water. Also, unlike positive displacement pumps, centrifugal pumps are able to take advantage of any incoming pressure on the intake side of the pump. This additional intake pressure will simply increase the discharge pressure of the pump. For example, class, if the pump is receiving water at a pressure of 60 psi from a hydrant at the intake side of the pump, and you need to supply the attack line at 100 psi, the pump will have to create only an additional 40 psi to achieve the desired pressure. Centrifugal pumps can be single-stage models with one impeller or multi-stage units with two or more impellers within one pump housing turning on the same shaft. A single-stage pump has one impeller, which both takes the water in and discharges it out of the same pump. This single impeller is responsible for supplying 100% of the total amount of water for the pump. This design makes the pump easier to operate because the pump can operate in only one mode. A two-stage pump is the most common type of multi-stage pump. It has two impellers, which are enclosed in their own pump casings but are part of a common housing. Each impeller is identical in size and capacity, and each is mounted on the same drive shaft and, therefore, spins at the same speed. At the discharge side of the first impeller, a transfer valve directs the water to either the pump's discharge header or the intake side of the second impeller. A transfer valve determines whether the pump will be operated in series/pressure mode or parallel volume mode. Both positions have their own strengths and weaknesses. When water is directed into parallel volume mode, it enters each impeller from a common intake side and is discharged into a common discharge header. This results in the pump's maximum volume of water being discharged. In this mode, each of the two impellers pumps 50% of the pump's total capacity. For example, class, if the pump is rated as a 2000 GPM pump, then each impeller would discharge a flow of 1000 GPM. When more than 50% of the pump's rated capacity is needed on the fire ground, the pump should be operated in parallel volume mode to ensure that the desired flow can be achieved. When water is discharged in series pressure mode, it travels through one impeller at a time or in series. Water enters the first stage pump impeller's intake side, gains pressure, and is discharged to the second stage impeller's intake side. The second impeller then pumps the water out of the discharge header. The water will have more pressure as it enters the second stage impeller than when it entered the first impeller, and it will gain additional pressure after being discharged from the second impeller. Series pressure mode is the position in which two-stage pumps are most commonly operated. Most fire responses do not require the pump to deliver more than 50% of the pump's rated capacity. Therefore, the pump is left in series pressure mode so that the desired pressure is achieved by operating at a lower rate or RPM. A fire pump is rated by and tested to UL specifications. To satisfy the UL standards, it must produce 100% of its rated capability at 150 psi for 20 minutes, 70% of its rated capability at 200 psi for 10 minutes, and 50% of its rated capability at 250 psi for 10 minutes. No additional rating is provided for pressures greater than 250 psi. Such pressures can be generated by using one pump impeller or multiple pump impellers inside the pump. Alternatively, the pump can be configured to provide pressure significantly greater than 250 psi by directing the water from the first impeller directly to the second impeller and then to the discharge, thereby doubling the pressure. With this configuration, 50% of the flow rate of the pump is lost because the first impeller does not send its water to the discharge side, but rather sends it to the second impeller. This is a control valve on the pump panel of a multi-stage pump indicating whether the impellers are being operated in parallel or volume mode or series pressure mode. If the pump operation requires a large volume of water, then the pump should be operated in parallel volume mode. In most pumping operations, you will supply one or two hand lines with a total flow of 300 to 400 GPM of water. A 1,000-gallon two-stage pump can easily supply this amount while operating in series or pressure mode. The advantage of this configuration is not attributable to any need for excessive pressure. This setting allows the pumper engine and power supply to produce the water at lower engine speed, which is more efficient. Think of a two-stage pump as similar to working from a hydrant water supply and pumper. When you start operating from the onboard water tank and pump water at a pressure of 100 psi, the total pressure available on the discharge is 100 psi. When the hydrant line is opened, it provides 100 psi to the intake side of the pump, which is combined with the 100 psi flow that the pump is already supplying. Therefore, the pressure will be increased at the discharge to 200 psi. The same concept class applies when water is directed from the first impeller to the second impeller instead of being allowed to flow out of the discharge. The pressure is doubled in the pump, but the total flow capability depends on the capability of the first impeller because the second impeller now receives its water from the first impeller. Special multi-stage pumps have been built to produce extraordinarily high pressures for special pumping requirements. In addition, some fire departments want to preserve the ability to use high-pressure booster lines while still having volume pumping capabilities of 500 GPM or more. One method of achieving this goal is to place both a piston pump and a volume pump on the same fire apparatus. Another approach is to use a three-stage pump. The first two stages operate as a two-stage pump as previously described, while a small amount of water is directed to a third stage that produces higher pressures, typically supplying one or two booster hose lines. Pump capacity over the years has increased significantly as larger pumps with larger impellers have been developed. In the 1950s, pumps typically delivered flows at 500 to 750 GPM. Today, fire pumps can flow water at 2,000 GPM or larger. The other element driving the increases in pump capacity is the increase in diesel engines' horsepower, which has doubled from 250 RPMs to more than 500 RPMs since the 1950s. To turn a pump fast enough to produce a flow of 2,000 GPM at 150 psi from draft requires a significant power supply, which is readily achieved with modern fire apparatus. Okay, class, let's take a look at a fire pump anatomy. The two main sides of all pumps are the intake and discharge sides. The intake side of the pump is where the water enters the pump. It is also referred to as the supply side of the pump because it is where water is supplied to the pump. On most pumps, the pipes and connections for the intake are set lower than the discharge piping and connections. The location where the water exits the pump is called the discharge side. Valves may be located on either side of the pump. They are necessary to control the flow of water both to and from the pump. Drains allow operators to empty the pump for repairs and to ensure that the water in the pump does not freeze in cold weather situations. NFPA 1901 further describes these components of fire service pumps, pump intake connections, and pump discharge outlet connections. Pump intake connections. Water enters the pump from either the onboard water tank or an intake connection pipe. The pipe that leads from the apparatus water tank to the fire pump is commonly referred to as the tank to pump. This pipe can be of various sizes, but must meet certain performance requirements. If the water tank has a certified capacity of less than 500 gallons, the piping and valve arrangement must be capable of delivering water to the pump at a minimum rate of 250 gallons per minute. If the water tank has a certified capacity of greater than 500 gallons, the piping and valve arrangement must be capable of delivering water to the pump at a minimum rate of 500 gallons per minute. The tank-to-pump piping also contains a check valve, which allows water to flow only from the tank into the pump and not back inside the tank. This helps prevent damage to the tank in situations where excessive intake pressure is encountered, such as relay pumping. When the internal water tank is not used to supply the fire pump, an external water supply is needed to fulfill this purpose. This water enters the pump directly through the intake side via an intake connection pipe. The pump should have a sufficient number and size of intake connections to perform the pump certification test successfully. Most common intake connections are national standard thread or sexless type connections, such as a Storz connector. These intake connection pipes are usually located on both sides of the pump. If intake piping were located at the front or the rear of the apparatus, that arrangement might not allow for drafting at the pump's rated capacity due to the length of the piping. Most pumps also include one or more valves connected to the intake connection piping to control the water flow at the intake to the pump. At least one valve should be a minimum of 2.5 inches nominal size. Most fire service pumps rated up to 2,000 GPM have a large diameter hose intake that is 4 to 6 inches in diameter on both sides of the pump. Several LDH intake valve designs may be used. As an example, a ball valve, a butterfly valve, a piston intake valve which is connected to the threaded intake piping. Each intake valve that has a connection larger than 3 inches must be equipped with an adjustable automatic intake pressure relief device installed on the supplier, the intake side of the valve, to bleed off excess pressure coming into that valve. The excess pressure is required to discharge away from the pump operator, and the valve should be adjustable from 90 psi to at least 185 psi. If the pump is equipped with one or more intakes larger than 3 inches that are not valved, an adjustable automatic intake pressure relief device must be installed on the pump system to bleed off excess pressure from the hose connected to the intake side of the pump. This automatic intake pressure relief device must be adjustable from 90 psi to at least 185 psi and discharged to the atmosphere and away from the pump operator. Each intake valve must also be equipped with a bleeder valve to remove any air trapped in the hose before it enters the centrifugal fire pump. All intake piping must also have a removable or accessible strainer to prevent debris from entering the impeller of the pump and causing damage to the pump. All intakes must be provided with caps or plugs and should remain secured to the apparatus when removed. This ensures that they will not be lost. The discharge side of the pump is where the pressurized water is expelled from the pump and distributed to discharge outlets. One of the outlets from the discharge side of the pump goes to the apparatus mounted water tank and is used to fill the tank and circulate water. These outlets have piping that is usually 1 to 2 inches depending on the size of the water tank. A valve to operate this discharge, called the tank fill valve, is located on the pump panel. Another outlet from the discharge is a pump cooling or recirculation line, whose operation may be either automatic or manual. This line, which is smaller than the tank fill line, is used to circulate water in the system to prevent overheating the fire pump. Discharge outlets of 2.5 inches or larger must be provided to discharge the rated capacity of the pump. Generally, class, a minimum of 2 2.5-inch outlets will be provided on any pump that is rated at 750 GPM or greater, and a minimum of 1 2.5-inch outlet will be provided on any pump rated less than 750 GPM. All 2.5-inch or larger discharge outlet connections must be equipped with a male national hose threads. This requirement is intended to ensure interoperability between fire departments at major incidents. The piping and valves supplying pre-connected 1.5 or 1 3/4 inch and 2-inch hose lines must be at least 2 inches in size. Any discharge that is not directly connected to a pre-connected hose line must be equipped with a cap and secured to the apparatus so they are not lost. Each discharge outlet must be equipped with a valve that can be opened and closed smoothly while operating at 250 psi. Each discharge must have a valve that can be operated from the pump operator's position and have an indicator to show when the valve is open or closed. Control of discharges may be achieved by pull-type actuators, swing valves, flexible push-pull controls, gear-operated hand wheel controls, or hydraulic, air, and electric operators. These controls may be either quick operating or slow operating. If the discharge valve is 3 inches or larger, it must be equipped with a slow operating control mechanism. All 1.5-inch or larger discharge outlets must be equipped with a drain or bleeder for draining off pressure from a hose connected to an outlet. A pump drain must be provided to allow the draining of the pump and all water carrying pipes and accessories. Fire department personnel must be able to operate this drain valve without getting under the apparatus. Let's now talk about the pump panel. The gauges, instruments, and controls necessary to operate the pump are located on a panel known as the pump operator's panel. Each gauge, instrument, and control must be marked with a label as to its function and must be illuminated for the operator to see it during night operations. NFPA 1901 requires the following controls and instruments be provided and installed as a group on the pump operator's panel: master pump intake pressure gauge, master pump discharge gauge, pumping engine tachometer, pumping engine coolant temperature gauge, pumping engine oil pressure gauge, voltmeter, pump pressure controls, pumping engine throttle, primer control, water tank to pump valve control, water tank fill valve control, water tank level gauge, fuel level indicator, and pump overheat indicator. The master pump intake pressure gauge is connected to the intake side of the pump. It measures both a positive pressure and a vacuum. It must be capable of reading from 762 millimeters of mercury vacuum to at least a gauge pressure of 300 psi. The gauge must be labeled as pump intake. The master pump discharge gauge measures the pressure as it leaves the pump and is connected to the discharge side of the pump. It must be capable of reading from 0 to 300 psi. It also must be labeled as pump discharge and located within 8 inches of the master pump intake gauge. It must also be at least 1 inch larger than all other discharge gauges. A pressure gauge must also be provided for each discharge outlet that is 1.5 inches or larger in size. They must be marked to indicate the outlet to which they are connected to. They also must be connected to the outlet of the discharge valve. There are 2 types of gauges that may be used, an analog gauge or a digital gauge. Analog gauges must meet the following requirements. The gauge must be resistant to vibrations, pulsations, corrosion, condensation, and shock. The master intake and discharge gauges numerals must be a minimum of 0.25 inch high. Numerals must be a minimum of 5/32 of an inch high for all other discharge gauges. The gauge must have graduation lines showing at least every 10 psi with major and intermediate gradation lines emphasized and figures at least every 100 psi. The gauge must have internal mechanisms that are factory lubricated for the life of the gauge. Digital gauges must meet the following requirements. Digital master pressure gauges must have an accuracy of plus or minus 3% over the full scale. All digits must be at least a ½ inch in height. The gauge must display pressure in increments of not more than 10 psi. A flow meter is a device on a straight section of pipe that measures volumetric flow rates, is threaded on each end, and is placed between 2 sections of hose. A sensing device on top of the meter measures the flow, or the gallons per minute, through the hose. In the fire service, these sensors are generally spring-probed or paddle wheel design. Flow meters give an indication of the actual volume of water being discharged through each line. This flow is sent as a signal to the gauge. The indicator gauge may be analog or digital. The use of a flow meter can lessen the amount of calculations required to determine the pump discharge pressure. It can deliver the desired flow without the operator knowing the length of the hose line, the friction loss, or the engine pressure. It has several advantages. Flow meters are very useful in multi-story buildings, as hose length, friction loss, and elevation vary in incidents involving these structures and may be undetermined. The flow from the master stream appliance with automatic nozzles may look good, but may be actually smaller than required. Flow meters eliminate this problem. Flow meters eliminate the math needed to carry out a relay operation because the flow meter is automatically set to the desired flow. Engine tachometer is an instrument used for measuring rotational speed, defined as RPM of the apparatus engine. The pump operator may reference a tachometer when troubleshooting any issue with the pump. Each pump will identify on a nomenclature plate the RPM required to pump a specific number of GPM at a certain PSI. If the PSI does not match the RPM of the engine, the operator may recognize a problem with the pump and have to stop its operation. The engine coolant temperature gauge and engine cooling devices indicate the temperature of the coolant inside the engine of the apparatus. If the temperature is too high, it can cause severe damage to the engine and possibly cause it to shut down. If the temperature is too low, the engine may not operate as efficiently. An engine cooling device may be installed to assist with maintaining the temperature of the engine coolant for optimal performance. The device uses the water from the fire pump when the pump is operating and directs water to cool the pipes that carry the coolant around the engine through an exchanger. This lowers the temperature of the engine coolant, thereby lowering the temperature of the engine. However, it may also raise the temperature of the water that is circulating inside the flow pump if no external water source is being used. The engine oil pressure gauge. This gauge indicates whether an adequate supply of oil is being distributed to all of the necessary areas of the engine. If the engine is not properly lubricated with oil, it can overheat and seize. Different engines operate at different oil pressures, so the operator must be familiar with the normal operating range for the oil pressure in each apparatus they operate. The voltmeter measures the voltage across the battery terminals and gives an indication of the electrical condition of the battery. Operating voltage while the alternator is charging may vary between vehicles depending on the regulator setting. Always refer to the manufacturer's operation manual to determine these parameters. The water tank level indicator. The pump operator must be capable of determining the amount of water that is inside the onboard water tank of the apparatus. This information must be visible on the pump panel, which usually indicates the water level in 1/4 increments. Some apparatus manufacturers may install large lights on the side of the apparatus so that the water level inside the water tank can be seen from a greater distance. The fuel level indicator. The pump operator needs to be aware of the fuel level of the apparatus. A fuel level indicator, or red warning light indicating when the fuel level falls below 1/4 of the capacity of the tank, must be provided on the pump operator's panel. The primer control. The pump operator must be capable of operating the pump's priming system from the pump panel. This device is used to expel any air that may be trapped inside the pump and during drafting operations. This topic class is discussed further in the chapter Drafting and Water Shuttle Operations. The priming system must be capable of operating with no lubricant or with a biodegradable non-toxic lubricant. The pump pressure control system is to control the discharge pressures and thereby protect firefighters who are operating hose streams. It also protects the discharge hose from damage in the event attack hose streams are shut off or other valves are closed, reducing flow rates. When multiple attack lines are flowing, they may be operating at different pressures. As one attack line is shut down, the excess pressure may be transferred to the other attack lines, causing the firefighters on the nozzle to lose control of the line. By using the pressure control system on the discharge side of the pump, the driver can ensure that the firefighters on the nozzle do not receive an excessive amount of pressure as hose lines are opened and closed. Two systems may be used to control the discharge pressure of the pump: a discharge pressure relief valve or a pressure governor. The discharge pressure relief valve controls pressure by passing water from the discharge side of the pump back into the intake side of the pump. The pressure governor controls the engine speed, which relates directly to the net pump pressure. If the speed is raised, the pressure goes up. If the speed is lowered, the pressure goes down. Regardless of the system used, NFPA 1901 requires the following. The system must be equipped with a means to indicate when the system is in control of the pressure. For the discharge relief valve, an indicator light on the pump panel usually accomplishes this. With a discharge relief valve, the light will illuminate when the valve is opening and dim when it is closed. For the pressure governor, a light or digital screen will show when the system is turned on and whether it is controlling the engine speed or the pump pressure. One person at the pump panel position must control either system. If the system discharges water to the atmosphere, the discharge must not expose the operator to high-pressure water streams. The system must automatically control the pump pressure to a maximum of 30 psi pressure rise no faster than 3 seconds and no slower than 10 seconds from the time the pressure surge is detected. The system must operate over a range of pressure from 70 to 300 psi discharge pressure and flows greater than 150 GPM up to the rated capacity of the flow pump. Pressure control systems will relieve excess pressures when the valves are closed in a normal manner. Some water hammer conditions could occur due to valves being closed so quickly that the system cannot respond fast enough to eliminate damage to the equipment. Proper fire procedures are still required. Pumping engine throttle. The apparatus engine powers the fire pump. In turn, the operator must have a way of increasing or decreasing the engine speed from the pump panel. the pump panel must be equipped with a throttle control that holds its set position to control the engine speed. Many older apparatus have a manual throttle control. Newer apparatus must be equipped with an electric throttle control or an electronic pump controller. Electronic pump controllers. In recent years, technology has reduced the amount of calculations that the driver-operator must perform. Technology is constantly changing the electronic systems found on fire trucks and has influenced the way the pump panel operates. Multiplexing is a term used in electrical engineering to refer to the process of combining information from several different sources. Class, in the fire service, this means that different sensors and controls on a pumper are brought to one control board or indicating panel. The trend in modern fire apparatus is to use electronic control and monitoring equipment. Many new pumping apparatus, for example, include electronic throttle and pressure controls. Electronic components are often designed by an independent contractor and integrated into the manufacturer's apparatus. Two examples are the electronic fire commander offered by Class 1 and the in-control mechanism developed by Fire Research Group. These companies provide a small computer panel, which consists of a keypad and display, for controlling the pump. Placed on the pump panel, these panels contain both a pressure governor and an engine speed governor and include the preset function that eliminates the need for a separate throttle or pressure relief valve. They also feature an LED information center that displays engine-related data such as temperature, oil pressures, speed, and voltage. A one-touch button advances the pressure to the pre-programmed pressure, and another button returns the engine speed to the idle level. If the pre-programmed pressure is not reached, the pressure may be increased or decreased by pushing an increased pressure button or a decreased pressure button, respectively. The concern that arises with use of this technology is the possibility of an electrical failure disabling the fire apparatus. The threat of an electrical malfunction is increased because of the frequent absence of manual overrides on fire apparatus with these features. The driver-operator must have a thorough understanding of the fire apparatus and pumping procedures should problems occur. Next class, I want to talk about power supplies for pumps. The simplest form of power supply is available with the portable pump. This pump is typically carried by 2 or more firefighters to a water source and used to pump water from that source. It has a small engine attached directly to the pump and provides power on a 1-to-1 basis. For every revolution of the engine, there is 1 revolution of the pump. There is typically no gearbox, clutch, shifting level, or other devices to operate. You simply start the engine and the pump starts. This same concept is often used for aircraft crash rescue apparatus so they can have a pump and roll capability. That is, the ability to discharge water as the apparatus is moving. Some fire apparatus may have a pump mounted on the front bumper, known as a front mount. The power for this pump is taken from the crankshaft on the front of the engine. It is transferred via a drive shaft to the pump transmission that operates the pump. This same concept is often used to power large snowplow trucks, cement mixers, and other heavy equipment. Power takeoff, known as PTO units, are commonly used for small pumps such as those found on tankers or tenders. This unit is mounted to the side of the transmission and through a shaft directed to the rear case on the pump. It provides a less expensive method of developing power to the pump, especially when the pump has only limited capacity. This approach also provides a pump and roll capability for apparatus such as wildland firefighting trucks. The most common power system found in pumps is the transfer case. This gearbox is mounted to the fire apparatus frame between the transmission and the rear axle. A drive shaft connects the fire apparatus's transmission to the transfer case so that the transfer case has the ability to direct the power to the rear axle or to the pump. When you place the pump into pump gear in the cab, you are transferring the power from the rear axle to the pump. The gear ratio is typically 1:1. The purpose of this configuration is simply to divert the power from one usage to another. The speed of the pump is directly related to the speed of the transmission. A transmission placed in first gear will propel the pump at a slow pace. By comparison, a transmission placed in fifth gear will turn it at a much faster rate. The fire apparatus manufacturer determines the most effective gear to use for the engine and the optimal transmission arrangement for each fire apparatus. The manufacturer must also consider how much power is required for the pump application. Automatic transmissions are specifically made for pumping operations that will lock into gear intended for pump operations once the fire apparatus is placed in pumping mode. This setup prevents the transmission from shifting gears and ensures that the pump operates only in the selected gear. This is typically the highest gear. All right, class, as we come near the end of this lesson, let me summarize it. As the driver operator of the pump apparatus, you must understand how pumps operate so that you are able to fix any problems that you may encounter on the fire ground. The pump panel is the most notable device on the fire apparatus. Once you have a thorough understanding of the pump behind it and the way in which the pump functions, you will be capable of confidently operating the fire pump. It is important for the new driver operator to understand that the fire apparatus is not like any other vehicle and, therefore, should not be operated like other vehicles. According to the NFPA, a pump is defined as a provider of liquid flow and pressure dedicated to fire protection. It is a mechanical device used to move fluids. The goal in firefighting is for the pump to move water from a source, such as the onboard water tank, to the fire through the attack lines. To do so successfully, the driver operator must understand how each different type of pump works. The fire service primarily uses two types of pumps: positive displacement pumps and centrifugal pumps. Each type relies on very different operating principles and offers a very different set of features. Positive placement pumps produce a flow by capturing a specific volume of fluid per pump revolution and reducing the fluid void by mechanical means to displace the pumping fluid. Two broad classifications of positive displacement pumps exist: the piston pump and the rotary pump. Centrifugal pumps are the most common fire pumps in use today. They do not flow a definite amount of water with each revolution. Instead, the flow or amount of water discharged is based on the pressures at the discharge side of the pump. The two main sides of all pumps are the intake and discharge sides. Intake relief valves prevent excessive pressure from building up on the intake side of the pump. Discharge relief valves prevent excessive pressure from building up on the discharge side of the pump. The pump panel consists of several gauges, controls, and valves to operate the pump. Okay, class, this concludes our lecture and study of fire pumps. If you have any questions, please feel free to contact me on my cell phone or by email, and I'll either return your call or your email within a 24-hour period. Thank you.